Hello dear students, welcome you all. In this lecture, I am going to discuss about the limitations of a nuclear shell model. So you can see here. In the earlier lectures, I have discussed about the nuclear shell model in detail. I have discussed all the applications and advantages of nuclear shell model, right? So in today's lecture, I am going to discuss about the limitations of this nuclear shell model. We know very well that this nuclear shell model was most successful in explaining many features of the atomic nucleus, starting from the existence of magic nuclei, spin and parity of the nuclei, right, their magnetic dipole moment, their electric quadrupole moment, all these properties, nuclear isomerism, all these properties were explained by nuclear shell model. So we can say it was most successful model as compared to the liquid drop model and Fermi gas model of the atomic nucleus. But still it have many drawbacks, many limitations. So I am coming to all of them one by one. The first limitation of nuclear shell model was that in nature there are some nuclei like 1H2, 3 lithium, 6, right, 5 boron, 10, 7 nitrogen, 14. Now these four nuclei you can see here, hydrogen 1H2, lithium 3, lithium 6, boron 5, boron 10 and nitrogen 7, nitrogen 14. These nuclei are stable nuclei in the nature, but neither these nuclei are magic nuclei, right? Neither there is a formation of closed shell. So why these nuclei are stable in the nature? So shell model has no answer to this question. It completely fails to explain the stability of these nuclei in the nature, right? So this is the big drawback of this nuclear shell model, that it is completely silent about the stability of these nuclei in the nature, right? So this is the first limitation. Now I am coming to the second one. We know very well that the shell model is capable of calculating the spin and parity of different nuclei, right? But if we look at the different nuclei in the nature and we try to calculate their spin and parity, then it is found that the predictions made by the nuclear shell model are only valid exactly in case of nuclei which are in the ground state, right? But if we go to the nuclei sorry, which are in the excited state, in that case the predictions or calculations of the nuclear shell model for spin and parity, they deviate from the theoretical predictions. The experimental observation deviate completely. It means we are not able to calculate spin and parity of the different nuclei which are in the excited state. It only predicts correctly when the particular nucleus is in the ground state, right? So this is a big drawback, because when a nucleon is excited to the higher energy state while leaving its on state, in that case this model failed to explain the spin and parity correctly, right? So this is the second drawback. Now I am coming to the third one. We know very well that the shell model was capable of calculating the magnetic dipole moments of different nuclei and particularly odd A nuclei. I have given you the formula for the calculation of magnetic dipole moment of a particular nucleus, right? But when we did the experimental measurements of the magnetic moments of different nuclei, then it is found that even in the case of odd A nuclei, right, the magnetic moments calculated by that formula, they does not agree with the experimental observations correctly. Although this model was able to make the rough predictions, or we can say predictions about the magnetic dipole moments, but we can't say that the magnetic dipole moments predicted by these models are exactly correct. There were deviations from the theoretical predictions. Large deviations were observed in case of some nuclei. So it means this shell model again does not make the correct predictions of the magnetic dipole moments of sorry, different nuclei, right? So this is again a big drawback. Now I am coming to the case of electric quadrupole moment. We know very well that the shell model is capable of calculating the quadrupole moment of different nuclei, right? And shell model says that if nucleus is magic, the quadrupole moment is 0 and it is exactly spherical. But if it is non-magic, then there is a possibility that it possesses electric quadrupole moment either equal to positive or negative, right? But when we use the formula given by the shell model for the calculation of the electric quadrupole moment, it is found that again there were large deviations in many nuclei because the calculated values of the electric quadrupole moment was not matching with the experimental results. So it means in toto or in nutshell we can say that although the shell model, nuclear shell model, make predictions about all these properties, but these predictions were not 100% accurate. They were accurate only up to 60 to 70%. We can say roughly that, right? Whether it is the magnetic dipole moment, whether it is the spin and parity, whether it is the electric quadrupole moment. So this is the list of major drawbacks. I have explained the 4 major drawbacks of this nuclear shell model, starting from the existence of these nuclei which are stable in the nature, then spin and parity, then magnetic dipole moments, and then electric quadrupole moment, right? So this is all about it. So thank you very much.